All right, so what we'll do today is get into chapter 3 of the book, which is dedicated to probabilistic reasoning. Last time we did chapter 2, which is propositional logic, which was the foundation for this. As you saw last time, what we had is in propositional logic, we had some kind of a set of worlds that were the different variable instantiations of a set of variables. And if you saw on this side, there was this notion of possible, not possible. So there was a classification of worlds as being either possible or not possible, depending on what we know. And what we knew was what we called a knowledge base, which was a set of sentences that ended up doing this classification. So now when we move to probabilistic reasoning, we're going to do something a little bit more refined. And in this case, we will have this basically notion of a degree of belief, as we discussed last time, which is a number in 0 and 1. And we were going to give a number in that range to each one of these worlds with the requirement that they add up to 1. This is now our notion of a state of belief, which is this mapping from worlds to these numbers as opposed to mapping from worlds to possible and not possible. Now the question is, in propositional logic, once we had a knowledge base, then the question was, is a sentence implied or not, right? Is alpha implied? Is not alpha implied? And as we saw last time, there was only 3 cases. Alpha is implied, not alpha is implied, or neither. Here we're going to have something more refined. We look at the worlds that make alpha true, and we just add up their basically weights. And the nice thing is we have a nice notation for this from last time. If you look here, we have this notation which says that sum over all worlds that entail alpha, right? You see the notation? And we just add these particular guys. And here's some concrete examples. If you look at this and you see the property of earthquake, we just added up the 4 worlds that make earthquake true, and we got this. And then burglary, not burglary, and alarm, all of these become easy. So now we have this basic notion of assigning a degree of belief to a sentence. All right, so you immediately get a number of properties based on this. You get a bound on the belief of any sentence. It follows immediately in this case that even though the probability of a world was between 0 and 1, but the fact that they added up to 1, now the probability of any sentence is between 0 and 1. And what's the probability in that case? It would be 0, because the sum would be over an empty set. And then remember what a valid sentence was. Right, it would be 1, because a valid sentence is true at every world, so we're adding all of them, and then you get a 1. And as you remember also from last time, that a world either satisfies alpha or not alpha, right? And therefore, when you look at the set of worlds and you look at alpha, not alpha, they partition the world. So when we add the probability of alpha and not alpha, what do we get? We got also a 1. And here's some concrete examples. Okay, now we want the probability of alpha or beta. And in particular, can we build this in terms of the probability of alpha alone and the probability of beta alone? Look at the picture up there. They may overlap. So this intersection area is being added twice, and you need to correct for that. So probability of alpha plus probability of beta minus their intersection. And here's basically a concrete example of, you see probability of earthquake, 4 worlds, probability of burglary, another 4 worlds, and then their intersection, earthquake and burglary, those are the 2, 1, and 2. And then finally you get the probability of burglary or earthquake, adding 2 numbers and subtracting 1. All right, so now let's do one more thing here before we talk about how we change our beliefs. So if look at this example, and if you try to compute what we call the marginal probabilities. So if you look at earthquake, and the marginal on earthquake is this. That is the probability of earthquake being true, 0.1, false, 0.9. And if you look at burglary, look what you see. And if you look at alarm, look what happens. What's happening as we go this way? We're basically becoming less certain. So if you look at earthquake, the distribution is skewed, right? 10%, 90%, then at 20, 80, and then almost 25, 75. So as we go this way, we're becoming less definite or certain about what's going on with that particular variable. You'll find later we will need ways to quantify this notion of uncertainty. Now, this is a variable that is binary. Sometimes you have a variable that has multi-valued, and it's not as obvious in that case to visually tell what's going on. So there's this notion that you may have heard of for doing that, which is entropy. So entropy is basically, in this case, it could apply to a single variable or multiple variables. In this case, we're doing it for a single variable x. And what you're doing here is, remember, in our notation, we're going to use a big X to represent the variable and small x to represent one of its values, right? When we're talking about a single variable. So this summation is over all possible values of that particular variable because it's summing over small x. And then you take the probability by log the probability. There's a negation sign. So this is basically entropy. And if we see for this particular example, look what's going on here. If you look at the entropy here, here it is for this guy, for that guy. So what happens? As we become uncertain, the entropy goes up. And this is an example of a binary variable. And in this case, what we're doing is the probability of x is p, and therefore probability of not x is 1 minus p, and you can see what happens to entropy as p changes. So as you can expect at the extremes, 0 and 1, where we're completely certain entropy is 0, and it gets actually to become at its peak when we're 50-50, right? That's basically entropy. So we have basically conceptually 4 segments today in our discussion. The first segment was, what is a probabilistic state of belief, right? And it is that table where we assign a number to every world. And that's known also as a probability distribution or a probability function. And we saw how if we have one of these tables, then we can assign a probability for every event or for every sentence. The other foundational question that we have to answer, how do I change a probabilistic state of belief when I receive information? So you have this particular table, and someone comes and says, by the way, I know that the alarm is triggered. So if you look at the table that we've seen, the probability of alarm triggering, I think, was around 24% something. But let's say someone comes and says, no, I know it did trigger. That happened. That event happened. And this is what we call beta up there. We need to update that particular table to reflect the new event, beta. And in probability, that is the notation used for that. So if we had PR as the initial distribution, the new distribution is PR given beta. And we say that the distribution has been conditioned on beta. So now what we need to do is see how this is done. Now, this is known as the conditioning. So this guy is the result of conditioning this guy on the evidence beta. Now, typically, you're given an equation immediately on this one, which most of you have seen probably. It's called Bayes conditioning. We're going to do it a little bit slower because we need to know what's going on underneath it. And part of the reason for this is we're not going to just be interested in this situation. This is what we will call, and people have called hard evidence. Hard evidence meaning I know for sure the alarm triggered. Done, right? Happened. In the second part, we're going to examine at some length the problem of soft evidence. The example given there, someone calls you and says, by the way, your neighbor, I think I'm hearing the alarm in your house. But they're having, maybe you know they have a hearing problem, so you're not taking that for granted. If you're conditioning on beta, right, so you know that beta really happened, we probably agree that its probability should be 1 afterwards, right? So the probability of beta given beta is 1, and the probability of not beta given beta is 0. By agreeing to this, you already did something. If you look at a set of worlds, and you divide them into those that satisfy beta and those that satisfy not beta, that already tell you all of the ones that satisfy not beta should be zeroed out. So for a whole bunch of the table, I know what to do, right? Zero out everything that negates the evidence. And what the first one is telling you for those other guys, the ones that satisfy beta, the evidence, now I have to change them so they add up to 1, right? Okay, so the only thing that's left is how do I change them? There's multiple ways you can change the numbers so that they add up to 1. The idea is when you go ahead and modify the numbers so that they add up to 1, make sure that you preserve this. What does this say? If you pick up 2 worlds that satisfy beta, and you look at their ratio, before you made the change and the ratio after you made the change, make sure that that's the same, right? There's no reason. I don't have any reason to alter the relative belief in things that satisfy the evidence. And in fact, if you do this, you've committed yourself to basically the following. That if you look at the probability of a world after I observe the evidence beta, then that is 0 if the world violates the evidence, and otherwise it is this. What is that? It's the previous probability of that world divided by the probability of the evidence. So this is acting now more like a normalizing constant. By the way, this guy there that you're seeing here, that we said we committed to it, it has a closed form, which is this. This follows from it. So if you're looking at an arbitrary, so that previous one was talking about worlds, but if you're talking about the property of an arbitrary sentence alpha given evidence beta, according to the previous equation, that's the following. Probability of alpha and beta divided by the probability of beta, which again, as I said, most of you have probably seen, and that's known as Bayes conditioning, and this is the formula we're going to use to update a state of belief in the face of hard evidence. Here's an example where we're conditioning on alarm, right? So I'm trying to, here's the original distribution, here's the new distribution conditional alarm. So you can see the guys that violate alarm got zeroed out and everything else was divided by 0.2442. Do you remember what that number was? That's actually the probability of alarm, must be, right? That's the normalizing constant. Good, look what happens here. If you look at burglary before, we call that the prior belief, that was 20% or 0.2. Given that I conditioned on alarm, the probability of burglary went up to about 74%. Makes sense, right? Okay. Now, if we look at earthquake, it was 10% and it also went up, maybe not by as much, it's now at 30%. That also makes sense in this particular case. There's a question that maybe we'll talk about later. This makes sense given the situation. How much of what you will be seeing now in the I'm going to show you some more dynamics of beliefs, of how they change when you assert evidence. How much of what you're seeing here is a function of the specific numbers that were put in there versus probability theory properties. That is, things that will happen regardless of what numbers you put, right? Remember our discussion from the first lecture about patterns of plausible reasoning and when people trying to capture human thinking and doing them in logic and so on. Okay, some of the stuff you're going to see is built into probability theory. You can't mess it up by choosing numbers wrongly, right? And we'll get to this later next week where you'll see exactly what's going to happen regardless of numbers, right? That part is pretty impressive, but you're going to get a preview of it next. So here's we condition on alarm. Let's go ahead and condition on earthquake now, right? So look what happened here. If you look at burglary, it was 20%. What happened? Still 20%, didn't change. So according to the state of belief, if I tell you that in the neighborhood there was an earthquake there, it says, you know, that will not change my belief at all in having burglaries. Nice neighborhood, but you can imagine another state of belief that would have a different property in this case, right? Where the, you know, having an earthquake may indeed change the property of burglary. And later, when you see how this particular state of belief was synthesized, it was actually generated from a Bayesian network. You'll be able to look at the Bayesian network and visually tell this. You'll be able to visually tell whether burglary and earthquake are independent or not. And if you don't want them to be independent, you know how to do this even graphically, right? So you'll have almost control over that. An ability to read the properties and an ability to actually change them to reflect your own or the domain that you have at hand. Okay, I just want to show you one more phenomena before we go on. The belief in burglary increases when accepting the evidence alarm, right? So we had burglary, and then I said, by the way, the alarm triggered. It says, okay, probability of burglary goes up. What happens when I know more, right? Beyond alarm. Probability of alarm, of burglary given alarm went up to around 74%, right? When we heard alarm. I came and said, by the way, there was an earthquake. What happened? Property of burglary. We have now an alternate explanation, confirmed, of the alarm. Correct? Makes sense? Okay. What if I get the confirmation that there was no earthquake? What's going to happen in that case? We will go further up, indeed. And that's what happens in this case. This looks like fun and simple and so on. You have to, if there was a time machine, you go back in the 80s and see what people trying to capture this. It was tough. It was really tough using other kind of techniques. Udeper called this the explaining away phenomena. And in his check out his book. It's a classic. It's outdated in certain ways, but in some of these historical discussions, it is still as current as it could be. Okay, folks. Let's do one more thing here on entropy. So if you remember when we did entropy, we said you have a variable and it has a distribution over it. What's the entropy of that distribution? And that was meant to capture the uncertainty of that variable. Now, here's an interesting notion, which is conditional entropy. Okay, forget about the equation for now, for a second. You have a variable x, and you say, what's the entropy? And here's the number. Then you go and say, by the way, I'm about to observe the value of variable y. I'm going to measure y, right? And then you say, what would happen to the entropy over x as a result? Now, here's the issue. I don't know what y will come out to be. I don't know yet. But I know I'm going to measure it. And I want to know what will happen to the entropy of x after I measure it. So the idea is you're going to say, wait a minute, what's going to happen to x? Let's say x is binary. It's going to come out either true or false. Let's assume it is true, correct? Then I'm going to get a conditional distribution. I'll take the entropy of that. I know how to do this. Then you say, okay, let's assume that y comes out to be false, right? That's another entropy. And then what do? You take the weighted average. I know what's the probability of y being true, what's the probability of y. That's basically it. This is conditional entropy. Now, here's the interesting thing. What happens to the conditional entropy x given y compared to the entropy of x? Okay, here's a surprise. It will not be higher. So by observing y, you either stay the same or will go down, right? And that means basically information cannot hurt. Information will not make you less certain. Information about y will not make you less certain about x. But you have to realize this caveat here. So even though the entropy or conditional entropy on x given y is less than or equal to the excuse me, conditional entropy on x, remember we had two cases? You said y could be true, and then you get an entropy. And y could be false, and then now the individual ones may go up or down, right? So it's possible that the entropy of x given a specific value of y may go, but their average will not, all right? And in fact, if you see in this example, you see this notion here vividly. Look at this burglary, right? Here's the distribution, here's the entropy, prior entropy. Now we want to compute the conditional entropy. Now we're assuming the alarm is true. So now I have the conditional distribution on burglary given alarms true. It's this distribution, right? Look at the entropy. What happened here? It went up. I became less certain here. But if you look at this guy here, under false, it went down, right? Now I became more certain under that. But if you actually look at the weighted average in this case, you'll find that it's this guy here. So it actually did go down. So we did beliefs, the basic probabilistic beliefs and some of the properties. We did conditioning on hard evidence. And now this third segment, if you want to think about it, is actually doing more on both of these. And we're going to start, this third segment has two parts. The first part is independence, a notion that many of you have heard about. What makes it particularly interesting and at the heart of a lot of what we're going to do is two things. One, if you have independence information, it's extremely valuable on many fronts. The very least is computational, meaning we will look at doing queries, and then if you want to compute or develop an algorithm for a query, and it's going to take that much work, if you have access to independence information, then you can make it run faster. And you can intuitively understand why, right? Because it will give you a license to break things and take a big computation and break it into independent computation and say, do this on the side and do this and put the results. In a sense, independence gives you a license to decompose. Okay. But the more interesting part is the following. Where do I get independence information? Right? We're modeling beliefs, and you would think that I would come to you and tell you, tell me, what do you know about independence? Write them down. You write a few equations, write more. No, it's not, that's not how it's going to happen. That's not what's going to happen. What's going to happen is, if we're doing the modeling, again, you build these networks and models in different ways, but if you're doing them by synthesis from other information by hand, I'm going to actually ask you about your perceptions about causality. I will tell you effectively, tell me what causes what. You know, like when we did that model for some of the ones I showed you earlier with medical diagnosis and so on, of here's the disease and so on. And then you will extract independence information from causal information, right? That's what's going to happen. So actually we will get causal information and get independence information from it. So the few things that we're going to say about independence is the following. There's a couple of equations that allow us to define independence, and a key property about them that you need to be aware of. The first one is, okay, so here's the concrete example. We have property of earthquake 10%, earthquake given burglary remains. So we say in this case that earthquake is independent of burglary. And the simple definition here is what you would expect, that the probability of alpha given beta is the same as the probability of alpha, that is alpha is independent of beta. Now, the key thing you need to know about is the following, and this is something that people may have seen this, and you probably not saw this particular definition. The classical definition you're given for independence is the probability of alpha and beta equals probability of alpha multiplied by the probability of beta. It's the same equation. You just have to move things around. But the thing that you need to be aware of is the following. The independence is not static. I don't know how many people have observed this when you studied this material before. Meaning, you may now believe that, or you view that alpha is independent of beta. But if I tell you gamma, that may change. They become dependent. And the other way around. So certain things, I tell you, does knowing beta change your mind about alpha? You tell me, yes, it does. And I tell you, but wait a minute, we also know gamma. You may actually tell me, no, it's no longer, it changes my mind. So let's look at the concrete example. You've seen it actually. If you look at, in this particular case, earthquake and burglary were independent, as we've seen, right? But look what happened. When I knew alarm, they were no longer independent, right? So in this case, burglary was 20%. I told you earthquake, it stayed at 20%. But in this particular case, when we know alarm, right, what happened? Knowing earthquake did actually change our belief in burglary. Okay, stare at this for a little bit. Right? Okay, let me help you visualize this. It will become clear next week when we do Bayesian networks. You need to look at the picture as a Bayesian network. Burglary, earthquake, and there is this child. The two guys are pointing to basically alarm. So alarm is a common effect. Okay, look what's going on here. Initially, the two causes are independent. And whoever did this causal graph did not put a link between them. So basically saying they're independent. I come and tell you, I know burglary, you say, oh, it doesn't change my mind about earthquake, or the other way around. Okay, but look what happened now. I came and told you the alarm triggered. The common effect of these guys triggered. Now they're interacting. See what's going on? So information about one changes your mind about the other. Pretty interesting in this case. But the point is, once more, they were independent, but due to new information, they became dependent. And there is another example. I'll just mention it, but you can read it and look at it in detail in the book, which is the opposite. Right? Things were dependent, and because of information, they became independent. And this example is about basically two temperature sensors, right? So you have two sensors. They're trying to detect whether the temperature is normal or extreme. And think about it. Don't look at this. It's like too many numbers there. It's in the book. Think about it this way. If I come and tell you one of the sensors is saying that the temperature is extreme, does that change your mind about what the other sensor will do? Yes. No? There are two sensors. One of them is saying, I think the temperature is extreme, right? Then you're thinking the temperature is probably extreme, that probably the other sensor will say that as well. So it does change your mind about what the other sensor will say in that case, right? But because, again, one of them is telling you something about the temperature, and that tells you what the other will do. But if I know for sure what the temperature is, then they're no longer dependent. So you can, again, look at the details in the text. This is the more general definition of conditional independence. Alpha is conditionally independent of beta given gamma. So gamma here is the constant before and after. That's the alarm in our example. I know alarm, right? And the question is beta relevant to alpha? So if you look at this side, there's beta. On this side, there's no beta, right? So in the concrete example we've seen, alpha would be burglary, and beta would be earthquake, right? And gamma would be alarm. And this is the definition of conditional independence. And this is the other way that you may have seen it written. Basically, what you have here is probability of alpha and beta given gamma, and look how it's decomposing into two independent computations, this guy and that guy, right? I don't know how many of you have seen this version of independence. If you get rid of the gammas everywhere, you get what you've typically seen, which is probability of alpha and beta equals the product of these two particular guys. Right, so this is what we need to say about independence. Now I need to tell you one more thing about notation, because when we get to next week and start talking about Bayesian networks, we're gonna have a new class of statements about independence. So what we've done so far is alpha, beta, and gamma are propositional sentences, right? It is more common in the area of probabilistic graphical models like Bayesian networks and Markov networks to make statements of the following form. And now we'll connect them to tell you what the relation. So remember, big X is a single variable. Big bold X is a set of variables. So we're talking about the set of variables X being independent of the variables Y given Z, right? So now these entities are sets of variables, and you write it like that. This is with respect to this distribution. X is independent of Y given Z. What does that mean? Again, remember notation. A small bold X is one particular instantiation of these variables, right? One particular settings of these variables. So what you're saying is, if I write this, I'm telling you X is independent of Y given Z for all instantiation X, Y, Z. So these small X, Y, Z, these are propositional sentences. Let's look at a concrete example. It becomes clear. If you choose the variables X to be the binary variables A, B, and Y is just a single variable, C, and Z is two binary variables, D and E. So remember, A, B, C, D, and E are all binary variables. They could be on or off. When you write this, when you basically write this particular guy here, what are you saying? You're saying all of these things. There are 4 states for the set of variables X, 2 states for Z, and 4 states for Y. That's 32 different statements, and here they are. A and B is independent of C given D and E. A and not B is independent of C given D and E, all the way to the last combination. Not A and not B is independent of not C given not D and E. Do you guys see what's going on? So that's a lot of statements. This is a very, very powerful statement here to say this. And in fact, when we look at Bayesian networks next week, we're going to understand them mathematically as making a bunch of declarations of this particular form. All right? So another way to look at it, that if you tell me what the state of variable Z is, you fix the state of those variables, then my belief on what the state of X is formed. And that will not change if you further tell me what the state of the variables Y. Does that make sense? That's what's going on, regardless of what the states are for X, Y, and Z. So remember this, we're going to get back to it, and this is how we're going to interpret these particular things. Okay, so one more definition here. And we finish this segment of 3A. This is the notion of mutual information. I'm just curious, how many have heard of mutual information before? Not too many. So the idea here, okay, a lot of equations, it's pretty simple. Again, we're going to do it for two variables, x and y, but you can do it between two sets of variables, set of variables, x, set of variables. Okay, so you look at x and y and say, what's the mutual information between them? Think of it as a way to measure independence. Independence, as we did it, is a yes-no question, right? The way we did it so far in the previous, okay, so I have to learn how to, if you look at this, I give you alpha and beta, say, are they independent? Either yes or no. But we need a softer version that maybe they are dependent but weakly or strongly and so on. Mutual information does that. And the way it is, okay, there is an equation up there, right? Mutual information between x and y, and there is this guy. Okay, don't stare at it. There is a motivation for this that you can probably look in the appendix in the book. But let's look at it from another angle. If they are independent, mutual information is going to be 0, right? Or it goes up. But look at how it relates to entropy. This is probably more informative. The mutual information is the difference. The entropy of x, given y, right? What does y do to change the uncertainty about x, right? And you can imagine it's symmetric. So you could do it the other way around, and it will also. So if y does nothing to the uncertainty on x, this is going to be 0. That's the independence. And okay, so this is this identity, which is an implication of the definition. It could be viewed as an alternative definition too. Maybe gives you an intuition of what's happening with mutual information. So it's actually a useful notion when you look at degrees of dependence or independence between things. It will be relevant in approximation algorithms that we're going to look at later. What I'm going to do next is just a couple of equations, and to try to close this part. They will be recurring later. One of them is known as the chain rule, and it's pretty simple. You can look at a chain like this, the property of alpha 1, alpha 2 all the way n, and you can write it like this. Alpha 1 given 2 through n, 2 given 3 all the way, and so on. You can see the pattern. It's pretty simple to remember. You can get this by multiple applications of Bayes conditioning, so it's really not a big deal. This is another significant identity or equation. If you've seen it before, you've seen it under the name of the law of total probability. I call it case analysis in the book. And the idea is if you have the probability of alpha, you can rewrite it like this as a bunch of other probabilities, alpha and beta I, where I ranges from 1 to n. The condition, though, for this to work is that these guys, the betas, have to be mutually exclusive and exhaustive. If you look at what's happening here with Venn diagrams, imagine alpha as a circle. And if these guys are mutually exclusive and exhaustive, what does that mean? They partition the set of worlds. So when you do this, you're partitioning alpha into a bunch of components that are non-overlapping and that cover all of alpha, right? That's the equation. Now you're going to say, why would this be interesting? As you'll see later, in fact, we have an example coming up. Computing alpha may be difficult, but computing these pieces may be easier. You may have the information to do this computation. And there's a version of this, which I'm going to show you in the next slide, which is perhaps more common, which is this guy here. So instead of talking about the probability of alpha and beta I, you do it like this. Probability of alpha given beta I multiplied by the probability of beta I. And maybe this is the more common version you've seen. It has intuition here, right? It says, look, these guys are cases. They are non-overlapping and they cover every possibility. So either I must have beta 1 or must have beta 2, okay, and they do not overlap. So what you're saying here is to compute alpha, let's go over these cases one by one. Assume that beta I happened. What happens to alpha at that case? What's the probability? And then I take the weighted average of these. Okay, let me just mention two specific cases here of this, and we'll take our 10-minute break. One example of these guys is to just take beta and not beta, correct? Beta and not beta are mutually exclusive and exhaustive. And if you do that, here's the first version. Probability of alpha is this, right? Probability of alpha and beta plus probability of alpha and not beta. And then if you look at the second case, it's basically, so you'll find this actually quite commonly used. Okay, so we have one more equation here, and it's this guy. We look at it and then take an example, and then we go to the discussion of soft evidence. Okay, so Bayes have his name in a lot of places, right? So it's Bayesian Networks, and then Bayesian Reasoning, and then Bayesian Learning, and we had Bayesian Conditioning, and now Bayes Rule. There's one more Bayes coming up. So you need to keep these sorted out, right? So, but there's a difference between Bayes Conditioning and Bayes Rule. So what's Bayes Rule? Bayes Rule says the probability of alpha given beta is this. Now, if you take this guy, probability of beta, move it to the other side, you get probability of alpha given beta multiplied by the probability of beta. That's alpha and beta, right? And here is just the other way around. Beta given alpha by, that's alpha and beta. Okay, it's really, you take Bayes conditioning, apply it twice, and move things around, you get this guy, right? And then, now the question is, how did Bayes get away with this? To get another name, another equation by just moving things around. I tell people, you can take your favorite equation and play with it and move things. You probably not get your name attached to it. There need to be a reason. Any idea why this is important? It even earned its own name. You want to look at this versus that. What it did is it allowed you to write alpha given beta in terms of beta given alpha. This is really significant. And the idea is sometimes one of them could be easier to obtain than the other. In fact, if you look at alpha being a cause of beta, right? So alpha is the cause, beta is the effect. In that case, this guy would be, what is the probability of the effect given the cause? And on this side, what's the probability of the cause given the effect? If you're looking at medical diagnosis, for example, it's the difference between saying someone has the flu, what's the probability that they will develop a headache? Versus saying, given that someone has the headache, what's the probability that they have a flu? Which one do you think is easier? If you're going to go to the doctor and ask them for one of these, they're more likely to give you effect given cause, right? Cause given effect is harder. And here's the classical, okay, this is a classic, right? You have to know how to do one of these problems. So it talks about a patient that tested for a particular disease, and we know that every 1,000 people has this disease. We also know that the test is not reliable, so it has a certain false positive rate of 2%. It has a false negative rate of 5%, and our goal is then to assess our belief in the patient having the disease, given that the test came out positive. Okay, it's very simple. Test has a false positive rate, false negative rate. We know that 1 in 1,000 have that particular disease. The patient did the test, came out positive. What's the probability that they have the disease? And we have two variables here. We have basically D, which is whether the patient has the disease, and T, the test came out positive. These are binary variables. So what we're trying to compute is probability of D given T, right? Whenever you have one of these problems, even though this sounds obvious what I'm going to say, it does make the difference. First of all, write down what's stated in the problem and equations. And before you do that, you have to decide your variables. What are the variables that I have? What do I know in the statement problem? And what am I trying to compute? Which is in this case probability of D given T. So here it is, right? This is the first thing we know. 1 in every 1,000 has the disease. That's the probability of D is 1 over 1,000. That's pretty simple. Now the false positive and negative rates, okay? So look at this. This is the false positive. What does false positive mean? The probability that the test come out positive given there is no disease, correct? That's a false positive. We're told that's 2%. Immediately from that, what do? You can get this. Not T, just 1 minus, right? So we already know this guy too, correct? Similarly, false negative. False negative is this guy. The test came out negative given there is a disease. False negative, we're told it's 5%, and immediately from that we get this guy, which is 95, right? So look, the difference between this and that is just the negation. All right, look, we're almost done, almost. What does Bayes' rule say? Bayes' rule says probability of the disease given the test is the probability of the test given the disease, da, da, da. This guy, we already know from above, it's 95%. We know probability of D, it's 1 over, correct? We're missing this guy. What is this? This is if you just put a guy from the population and do the test on them, what's the probability that it will come out positive, right? An average individual. We don't have that number. What do? Case analysis. Case analysis, exactly. And the case analysis in this case tells us that this guy is T given D by the probability of D, T given not D by probability of D. We know all of these quantities from above. We plug them in, and here you go. The probability is actually about 4.5%, right? Some of you may be surprised by this number. It looks too low, and it's too low. You think it's too low? Think it's too low? Surprised? Okay. Wait till we do sensitivity analysis. Sensitivity analysis, you say, wait a minute. I'm not paying for this test. If someone is testing positive and it's 4.5, I don't want to pay for this test. And this says, okay, I can sell you a better test, right? And then I can raise whatever these numbers, and then the question is, what can I pay? Sensitivity analysis, you would say, I want it to be at least 50%. Tell you, what should the false positive and negative rate be for that to happen, and so on. Quantitatively, and exactly will give you that kind of, even more sophisticated kind of reasoning, but for that you have to wait till later.